That is $300,000 disappearing in 400 milliseconds. Boom, gone. This exact bug reentrancy is what killed the DAO in 2016 for $60 million. It's the same bug that drained Fei Protocol for $80 million in 2022. And today, my AI just found it in 5 seconds. In 2026, nobody writes smart contracts from scratch anymore. We manage agents. So today, I'm running an experiment. I'm using Google Antigravity to pit 2 AI agents against each other in a fight to death. The first agent is victim agent. Its job is to build a bank, but without a door. The other one is attacker agent. Its job is to find one line of weakness and drain every single way and way out of that contract. I'm just a referee. Let's see who wins. So as you can see here, I have already opened up my Antigravity IDE. Now start the clock, because I'm gonna initialize a blank Foundry project. But I'm not writing the smart contract myself, not today. I wanna see if an AI agent can build us a bank that it doesn't know how to protect. So I'm gonna go ahead and say forge init. We have successfully initialized a new blank forge project, or Foundry project, as you may call. So let's go ahead and open our agent manager, and in here I'm just gonna go ahead and write a prompt for our AI to proceed with. Let's say write a vault.sol in src, allow ETH deposits and withdrawals, keep it simple, no open Zeppelin, and no reentrancy guard. You should not be applying the CEI pattern as well. And let's see what it is going to do. Okay, it analyzed our directory, it's generating something, it's thinking basically. We don't have to read this out loud, and as you can see here, it's being opened up automatically for us, the vault.sol. Okay, it says I've created the vault.sol file as requested. It includes a deposit function and a vulnerable withdraw function that deliberately performs the external call before updating the balance, violating the checks effects interactions pattern. Okay, perfect. So here's the file content. As you can see here, we have a mapping of address to uint. So here we are keeping track of balances of each address that exists in our smart contract. We have 2 functions, deposit, which is payable. We're gonna add the message.value, which is the amount of Ethereum being sent to deposit function, to balance of that message.sender, which is someone who is calling deposit function. And finally, we have withdraw function, which is unprotected by any kind of reentrancy guard, and it's not following the CEI pattern, which is perfect for our scenario. See guys, actually my instructions are specific: build a vault, handle real Ethereum, but here's the trick. I told it to keep it simple. In crypto, simple usually means dangerous. I'm practically begging it to leave the door unlocked. Now, the next thing we are going to do is that building the project. Let's accept it. Let's go ahead and say forge build. And as you can see here, compiler run successful. So we have built our vault.sol project. That is fantastic. As you know, code is useless if it doesn't run. So I'm spinning up Anvil. This is a local Ethereum blockchain running on my machine. 0 latency, instant blocks. So as you can see, these are wallets, these are private keys, and this is basically Battlefield, right? So in order to deploy our smart contract to our local blockchain called Anvil, we need something called a script. As you can see, we have it right away in here for counter.sol, which we have this contract. But before doing this manually, let's get rid of these first and open up our agent manager again. So the next command I'm gonna tell is that create a script so I can use to deploy my vault.sol contract. So he says to deploy the vault contract using the script I created, you can use forge script command. Okay, so we have forge script. Then we're going to specify the script that our AI just wrote. Then we're going to use an RPC URL, which we need to specify the URL. In our case, it's going to be this URL, which is related to our local blockchain Anvil. Then we're going to specify private key, which is the owner of the contract, and then -- broadcast. It's even giving us explanations on what each part is doing for us. That's perfect. For example, -- broadcast means that it actually broadcasts the transaction to the network. Without this, it just simulates the run. Okay, great. And finally, it says if you are testing locally with Anvil, you can just run this command. Wow, it just gave us the full command. We don't even have to write the RPC URL or private key ourselves as well. So let's go ahead and just copy this. And now I'm gonna paste this here and let's hit enter. Okay, it says client error, TCP connect error. As you can see, that's because I just stopped Anvil. So let's go ahead and create a new terminal. And I'm gonna open up Anvil. And then I'm gonna paste the command again. And as you can see here, we have our script ran successfully. And we finally deployed our contract to Anvil with this contract address. That is awesome. Now it's time to test our functions, right? So in here, I'm gonna say, let's test our functions. I wanna deposit to Ethereum, and then I'm gonna withdraw them ASAP. So give me the commands to do so using terminal. Let's see. Let's give it a wallet address. So I'm gonna say this is my wallet private key. This is my wallet address, and this is my smart contract address. Let's see. Which is deployed on Anvil. So here are the cast commands to interact with your deployed vault contract. This calls deposit function and sends 2 Ether along with the transaction. So we have cast, which is the built-in Foundry tool to send transactions to a blockchain. Actually, it's perfect for working along with Anvil, and it's just gonna use terminal. So it says cast send. Let's see, this is our contract address, deposit function -- value, which is 2 Ether, and the private key is gonna be this. Let's see, this private key is actually the private key that we're gonna use it to deposit Ethereum, right? And then -- RPC URL and our RPC URL of local blockchain, which is Anvil. So let's go ahead and paste that in. Okay, so it says success. So the operation has been done successfully. Status is success. We can go ahead and continue. So the next thing our agent tells us is that we can check the balance. You can verify the deposit was successful by checking the contract's mapping for your address. So let's go ahead and do that, huh? Okay, we're getting 2e18, which means 2 multiplied by 10 to the power of 18, which is exactly how we measure Ethereums on Solidity. So we get 2 ethers, which means that our previous operation has been done successfully, like for real, not just by checking this success status. So the final thing we're going to do is that we're going to withdraw our 2 Ethereums. So let's go ahead and say cast send. And as you can see, okay, we got success again. And if we go ahead and check our balance again, we can see that we are at 0 at the moment. So great. Now our deposit and withdraw functions are working seamlessly, although they are not protected at all from a security researcher perspective, but we can go ahead and continue for a moment. So the bank has been built. We think it's safe. Now we are bringing in the breaker. This agent that I'm working with has one simple job: read the code, find the mistake, hack the smart contract, and take the whole money. So let's go ahead and give it a prompt. I'm going to say analyze the contract of Vault. There is 100 ETH in that contract. Write a Foundry test file that uses Reentrancy attack to drain the entire balance. Let's hit enter. I'm not giving it hints. I'm not pointing to a specific line. I'm just telling it there is money here. I want you to steal it. This is a prompt that should scare you, actually. So it's constructing the test file, as you can see here. Okay, so it says the goal is to demonstrate reentrancy attack on Vault contract, which currently update the user's balance after sending Ether. So it's creating the Vault reentrancy.t.sol, which is how you create a test file in Solidity using Foundry. Alright, perfect. Here's our reentrancy attacker contract. As you can see, the agent is using a vault.sol file, which is the contract we just wrote. And it's gonna take a vault instance, actually. You can deploy one in the test contract, like I think in setup function. Yeah, as you can see here, we are deploying new instance of our vault contract. And then we are using deal function of VM, which actually funds the vault with 100 ETH to simulate existing users, right? Now, from this step now on, our contract is gonna have 100 Ether inside of it. And then we are using test reentrancy attack function, which is a test function in Solidity and Foundry. And in here, we are giving attacker 1 Ether. The attacker is gonna use attack function, and the attack function, it's gonna actually use the deposit function of our vault contract instance, and then it should get 101 Ether. It should drain all the money, including the money they deposited themselves, right? I'm gonna use force test, and as you can see here, let's see. Okay, one passed, test is successful. So vault balance before attack was 100 ethers, attacker balance was just 1 ether, and vault balance after attack is 0. So the whole protocol has been hacked. And finally, attacker balance after attack is 102 ethers. So why is that? Why is 102 and not 101? First of all, indeed, 102 is greater than 101. And since we are using cert GT, which stands for cert greater than, all tests are passing, which is totally fine and okay. But here's the thing. As you can see here, we are giving the attacker 1 ether to just try to attack. And now the attack function itself is using its own payable thing, right? So 1 plus 1, it's 2. And finally, we are depositing the 1 ether. The attacker has 1 ether, so it's 2. And the contract has 100 ether, which makes up to 102, which is the attacker balance after attack. So it worked. We just hacked a simple protocol using AI. And by the way, the protocol has been written using an AI as well. Alright, we hacked the protocol, but how? How does this whole reentrancy and stuff are working here? First of all, guys, let's get back to victim contract, the vault. As you can see here, it has a deposit function to put money in and a withdraw function to take it out, right? It's very simple, right? But look closely at withdrawal function. First of all, we are checking our balance, then we send the ether, then we update our balance to 0, right? This is the fatal flaw, because it sends the money before updating this state. So we can easily hijack control flow, right? So to exploit this, we wrote this Reentrancy attacker contract. It has a special function called receive function. In Solidity, this function runs automatically whenever the contract receives ether, right? So here's what's happening step by step. First, we deposit 1 ether into the vault. The vault records attacker balance 1 ether, right? Then we call withdraw function, this function, right away. So when we call this function, as you can see, we are using this message.sender.call fatal flaw. Okay, the contract, the vault contract, is sending us an ether. So guess what? Our receive function triggers. But here's the catch. The vault function still thinks our balance is 1 ether. You may ask why? Because this line has never run. That's it. So the withdraw function thinks our balance is still 1 ether, which is correct because our balance has not been updated and it's still 1. So this is the infinite loop that breaks the law of vault smart contract, right? So at the end of the day, the vault sees our balance is still 1 ether, so it sends us another 1 ether, and this repeats in a loop until the vault runs out of gas or funds. Only after the vault is empty does the original withdrawal function finally finish and set our balance to 0. But by then it's too late and we have already drained everything. So as a conclusion, we started with 1 ether, we drained the vault's 100 ether, and we got our 1 ether deposit back, and the total loot is 102 ether. This is why you always use the checks, effects, interactions pattern. First of all, update the state before making the external call. So the true pattern would be something like this. First of all, update the state and then do the external call. So what did we learn? We learned that history repeats itself. The code the DAO wrote in 2016, yeah, it looks almost exactly like what my victim agent wrote today. If you don't know what you're looking for, AI will just generate vulnerabilities for you. I don't want you to get hacked. So I've put together a GitHub repo linked in the description. It has the source code for this video. But also, I'm gonna provide a full breakdown of the worst reentrancy attacks in history, including the DAO and other ones, and exactly how they could have been fixed with one line of code. I'm gonna provide the link to that GitHub repo as well. So, end of the story for today. The victim agent failed. It built a glass vault and the attacker shattered it. But next time, who knows? Let's see what happens. So if you want more, hit subscribe button and you don't want to miss the next war. Promise. So, hope you're doing great and see you in the next video.